Welcome back to High Performance Computing. We have our practical lecture 2.1 and the second part of it. The first part was about MPI messages, and then we essentially learned with this also the MPI environment first, MPI init, and so on. Then we had simple point-to-point communication already in the last part, and then transformed over to some collectives where I showed them the broadcast for an example. We also try to understand a little bit with all of this, the differences between the job script again versus C code. So this is an important facet of it, because here we're thinking about that we can do changes to the C code, then we have to recompile. But we also need to think about that some of the code is hopefully written in a way that it's just scalable. So that means, in other words, the job script can then steer how many processes, or really how many tasks, I execute out of this one source code. And this is usually the problem for students. So understanding that, again, the same source code is used for all of this, hence the idea with the ranks. Right, so with the ranks, this gave us the opportunity in the first part, what we did with a ping pong, for instance, to identify who of the two ranks now being part of the program, of the parallel program, who is taking now the part of the ping, and then who is taking the pong back. This is not totally obvious, and you have to really look a little bit into the lecture part the last time, so part 1 of lecture 2.1. if you not really have understood this yet. Because what we will do now in the second part of lecture 2.1, we do much more practicals again, as usual as a practical lecture, but also we will go to more advanced material. So many of the things I was just putting into part, let's say, 1 of this lecture is really basic, and we cannot go back to every single detail. But you will also see that the application logic we will have now with non-blocking communication, we have Cartesian examples, but then also move almost towards a fishing simulation or the boat simulation over the ocean, where we try to understand what is, when we can have in a loop, then this Cartesian communicator used to basically simulate over time steps, a movement from the boat, or information exchange more accurately. So all of this is quite a comprehensive lecture, again, based on student feedbacks that were, let's say, giving us a hint every now and then. We have lots of repetition, and we try to remove that here a little bit now with this. Hence, let's fasten your seatbelt for an interesting lecture, starting with non-blocking communication. If you remember, we had already some aspects in lecture 2 about it. So the basics, I will not go into too much detail. But what we have essentially learned from the beginning of the MPI lecture was there's this blocking MPI send. And when I'm inside this, I don't do anything else. I just execute this function, and there's nothing else to do. And I'm waiting, because you have learned in point-to-point communication, I need a matching receive. Someone has to listen. Right, so basically this is blocked until someone is executing the receive, and with this you basically are stuck in your source code, cannot do anything, assuming that, for instance, here is a late sender. Here it's the other way around, so someone is actually listening since a long time in a blocking way, so can do nothing else, and waiting. And this is the thing that we want to avoid, the waiting times here. Because essentially that means idle time, right? I don't do anything, I'm just waiting for the MPI send to come. And this is a possibility now to combine essentially with different ways with an I-send, non-blocking communication, and an I-receive that you see here as a, let's say, non-blocking receive. But the non-blocking then introduces something what we call MPI wait or MPI wait all, that I also show you best in practice. So let's go to some practical example where we can say, that this is often used in different programs. You will see that the MPI I send and I receive, I will give you at the end of this lecture, indeed, as an example, when we have understood the Cartesian grid, that you have there, from one of our previous lectures, we said, if you want to have the ocean simulated, we would put a Cartesian grid in the ocean. But this is not everything. We also have to find out how we can use this Cartesian grid then for communication And in this communication, this non-blocking communication is quite useful, right? But before we go into the material of this, let's understand first non-blocking communication as such. It was a, let's say, small example. And then we move over to the Cartesian grid, because it's also not completely obvious to you, because that's also a new communicator, right? So we come to this step by step. The communicator was always MPI com world. That's what we know. And suddenly we have a new communicator. And this is something also we go stepwise. And then finally, when we have built on these concepts, non-blocking and the Cartesian card simulator, basically, we can go to a real application, sort of where we can per time step, give information to the surrounding grid, which is important to understand there. Let's say variables. Examples might be the fish population. We know which fish is swimming in which direction and is increasing the population there. But it could be also the other way around. What fish population is actually coming to my tile in order to simulate the fish swarms, for instance. But could be also, let's say, boat or not boat, could be any other variable. But let's go step by step. Let's start a little bit with non-blocking communication. And as this is a practical lecture, let's go back to Elia. So what you see here is that are already logged in. So I also want to not redo this now again and again and say, well, okay, we have logged in the SSH. You know by now how to do this on Elia with your username, with the SSH key, and you also will learn this in the first assignment how to do this yourself. So let's go directly into the non-blocking example here that I prepared for you. And when you look in the C code, it's quite an interesting conversation. It's a little bit reddish here because it's around the text. So we start a little bit with the usual things you already know: init, com size, com rank, right? So this is something which is, typically not a problem at all. And the same I've also here for you in the source code text documented what is actually happening here. And depending on the different, let's say, rank information, now we have two players here. We say rank 0 is, the first player, and then you will see lower, we have also an else part, which is else if my rank 1. So if it's the other processor, I do something. So here we want now to understand this idea that when I do something like ascending, right, then I want to continue with something in my own source code while already sending, something to the other source code execution, hence the other rank. And this is nicely best put when we do a printf here. You see essentially here's someone talking and start talking to the other, task that, here, please do not send any more messages, please send money instead, etc. This is something what the thing is going over the wire here. It's just a sort of funny example I got from, some tutorial here. But the key message to take away is that we send this now essentially as a buffer, right, that we have defined here. And in this buffer, we essentially address directly our, our rank. And we do this in the MPI com world. We will later do this communicator aspect then with the Cartesian, but here we remain in MPI com world, so things we know. And the beauty is also we get some information out of the requests, the MPI request here that you can define, and also the MPI status gives you then information that is essentially then binding these requests that you fire up in this, let's say, non-blocking sense, so that the wait basically gets a connection and waits until these requests are done. So in a way, it's a synchronization aspect here, right? So you can have multiple ISENs, obviously, because you see I can continue with the source code, right? Printf, hello there, I've just started the send, and I have a good time relaxing. So in other words, I can do something. I'm not stuck in a blocking send. But in order to do so, I need also at some point in time in my program a synchronization to say, well, now it's another time step, or something else is, that we don't want to lose a connection too much between the different power processes. And there, it looks like the message has been sent, because here we see the MPI wait is now the synchronization, waiting really for the request that has happened. So in other words, we know now, okay, the receive was actually executed or it was received. And this is just for, let's say, bugs if there's a problem. And then the second part is now the other role, if you want, right? So this is again showing us, you know, hi user here, but of course I receive it, but I also do something. I started this receive and I'm having a good time relaxing. So basically nobody waits for each other until, of course, they get then to the MPI wait request. At that point in time, we need to basically see that we have actually had the matching send giving us something in the buffer. And then, of course, we want to see what we got in the buffer. You see that a bit here with the get count, MPI get count from the status, how much characters were inside that we will print out here. And also the rest is just more or less for bug fixing here. So MPI finalized to end this, but let's also go a little bit back to the practical. So this is a source code. It is already compiled. Then we want to look what we do in the submit script. There's also no big surprises. We have 2 players, so 2 tasks. It is a little bit hard-coded in this example, just to make the case of this non-blocking example, but that doesn't really matter. As you know, in bigger programs, you probably don't do this. And when we come to the Cartesian example, we will see also that this is not always so easy. We have applications that have a certain, let's say, application domain that we want to parallelize, and that's something also which you will learn in lecture 3. But essentially, we can now execute this example. We got a, you know, job ID back. It's so actually queue. It's so fast that we again don't see it in the queue, but we assume there's an output. And when we look into the output, we probably have a nice conversation. And you see a little bit here what we had also in the source code. I just started this receive. You see the receive comes first, although honestly speaking, this could be also because it's all written in one file, sort of race conditions around the file. So sometimes it could be also that the send maybe is here first. But I'm having a good time relaxing, and then there comes a sending, but I'm having a good time relaxing. And basically, it looks like the message has been sent, and you know, it looks like 128 characters just arrived. And this is a text that was actually initially come out of the, let's say, rank 0 that wrote, you know, to task 1, or if you want, task 0 wrote to task 1, and essentially this was going over the wire. Or in other words, via the non-blocking send and receive. So admittedly a trivial example again, but it captures the essence of this non-blocking communication. So, and this is of course something we want to use later again. So we will have a more advanced example also later. Let's advance a bit in the slides. Literally what I actually sent here, you know, in the example and so on. I think this is all what I described already. You have also here the typical way how to do it, right? I avoid here again the compilation, as you know. This is basically always similar, and you don't need to necessarily always, you know, compile. Also, when you load the modules, you have learned this. You know, I have done this already in the first part, so the modules were still there when I would compile. And then you don't need to necessarily do this. As you have seen, I could just submit the job also. Now, when you log into the machine, that's different, right? So it's fresh, then you basically have to load the module in order to compile it properly. We looked in the output, we saw the message going basically to task 0, no, to task 1 from task 0, 128 characters with I send and I receive. With 2 players, all what I basically explained. Now let's advance a bit and think about communicators again. So this is very interesting material. It doesn't have to be the Cartesian communicator. You can create your own subgroups if you want. What is shown a little bit here, you can actually create a communicator group 1 and group 2. The interesting thing is that in the MPI-Com world, no matter how many other groups you form out of these processes, they will always have the same rank information like MPI-Com world in one particular communicator, and this is the MPI-Com world. So hence, this will remain the world of all processors. Just because you create a new one, is the rank information new in the new communicator. Hence, when you now create COM1 and COM2, and you will, do the message exchanges within the world of this communicator, they get new assigned ranks from 0 to 5, 0 to 4, because here we have 5 and here we have 5, 0 to 4. But these are not the same processes anymore because we are in the space of these different communicators. And for the communications, you will have to specify COM1 and COM2 for these groups. However, parallel to this will be always MPI COM world existing, where you basically get still your unique rank in the world of all processes. So when we create a new one now, we're thinking about message exchanges again, but in a more, let's say, structured way, in a more, Cartesian grid, as it is called. And I mean, you can see that a little bit in the ocean example here very clearly. What happens if you want to have a boat, basically going over the ocean, or a wave propagation of some height that we want to calculate over a certain ocean, the fish population over a certain ocean. So different examples here that, basically mimics the same thing, that we want to have information exchange propagated through the grid. And by doing this in a much more systematic fashion, we can specify already the application domain, like the ocean here, and assign them, let's say, different areas of the ocean, for instance. And hence you have something we call here rather an array, right, that we mathematically want to look on. So in the way that is here explained, this example is, of course, a 3 times 4 ocean part, right, that you see maybe not really here fully. This is more, but, think about that we are now here in the ocean. Now you have your different ranks. This is now the interesting thing when you create it. This new, let's say, Cartesian communicator will have this rank structure. And then, of course, we can suddenly talk about rows and columns, right? You see here row 0, 1, 2, and so on, and column, 0, 1, 2, 3. So, and then the source and destination is now something which means when I do a, let's say, periodic sort of, communication idea over, let's say, a for loop or some time interval, you see that I would like to have something like a shift done here, right? You want to shift the information. But what you also see is now I need to know who is actually my next partner when I shift here to the lower part, right? Hence, the source here is 8, where I will receive something from, but also I am basically sending to the 4 in the next time shift. And that's how you come to this information exchange over time, mimicking here maybe also the red arrows, right? Over time, over the ocean. And that's where you have this conceptual view of this communication with a Cartesian grid. And of course, by having this communicator, the beautiful aspect is that I can understand, where I am in the bigger field, and I can understand when I want to perform a shift in a certain direction. Then the MPI environment gives you source basically and destination automatically. You don't have to really program that of sort. You will know in a sense from the environment what are the kind of coordinates. And this is perhaps better explained when we go to some practical examples. So here I wanted to show you this example. Leave the non-blocking. And we enter the world of the Cartesian. Admittedly, it's a little bit more already complex material. Hence, you will see the source code getting more complex, more and more, especially when we have the other Cartesian example. So when we come here, we have the usual things you already know. I stop repeating it now. We said the dimension should be 3 times 4. We said periodic, that is sort of a switch on or off, and we want to have it in both periodic. In other words, you see that here a little bit, that when we are at the end, we still want to continue, and at the beginning to make it a really proper simulation. And then we already at something, what is here the MPI communicator. So we define a new variable, which would be our new communicator next to the MPI com world baseline that we established, right? We have an MPI status to obtain some status information later. And you see that we, out of this MPI-COM world, the world of all processors, we create now with MPI card create a Cartesian communicator, which has exactly the kind of properties that you see here, and that you also see will be stored in this communicator to the MPI communicator. Hence, in other words, if I now want to use, let's say, this communicator, or I want to use information exchange like a broadcast, I don't use any more MPI-COM world. I use now COM2D to do something, right? Because we are now in a complete different world. Again, just for you to understand, coming back to these beautiful pictures, we have created something like this, a subgroup where a new world lies, right? It looks more rather than this, like a Cartesian world, but still MPI-COM world is existing. But whenever I do communication exchange like here, in this Cartesian grid, I have to now actually have this COM2D to basically use in my information exchange. So that is one thing. And before we come now to really information exchange, you see also how nicely this MPI card coordinates helps us to obtain now the rank information based on these coordinates where I am in the Cartesian grid. So this is another nice function coming out essentially out of the out of the Cartesian world, or out of this power that I have really from this communicator. And then I can try to find out, and this is now an interesting element because it suggests now that we shift something, which is not true. It's just we want to understand what would be the source and the destination if we do it, right? Let's say, and this is something which is now the important aspect to understand. The shift is just preparing the message exchange in terms of finding out who I am in the bigger grid and to who I want to send when I do this in a certain, let's say, direction. You see that then basically here two variables that we want to get over with. And here we use this destination, right, where we want to basically do a send and receive. This is also possible with one, let's say, command. And then we use the MPI int here because essentially we have just an integer that we want to send around. And because this will be now executed, the source code from top to bottom, we start with MPI-COM world. Here we have suddenly a complete new one, COM2D. Hence, when we wanted to do the send receive in this new world, in this COM2D, we also have to specify this coordinate, this communicator there, and then get the status basically. And then we can here, give some information out. The rank is this, and the source is this. And then the destination is, based on this, the information that we essentially automatically receive here from, the idea of shifting that we then used also. But the shift itself, again, didn't do the shift. It just, or didn't shift the information really. It was still, one of our message exchanges. And I think the best is to explain it when we run it. So we will have, the submit card example shortly. And now we see that could be run on, 12 nodes, 12 tasks really, if you want, right? A task in a node. So why we do 12? 12 is very obvious. I think 3 times 4, because now what we sort of simulate in parallel computing here with a big simulation, the ocean, would be that we need, in order to, compute the fishing population or the boat movements or so, in this manner. So we have a 4 times 3. In other words, as we know, every rank, of course, needs a processor. So by specifying the 3 times 4 hard-coded in the source code, we lose, of course, now a little bit the idea of being flexible. Hence, we need 12 processors, and we can imagine what happens, and I will demonstrate it when we do just 11. But do now 12 here, I think, is our way to go in the beginning. We dispatch it quickly to see how it works. Also, this example is so fast, you see it's almost already done when we already want to see the output. And now when we see we have this 12 processors, executing exactly the same source code, but being in the same coordinate system, right? So everybody is involved in the MPI world. But we see now exactly these different ranks. They all write their output and get the information from the shift that I had basically here for you as a conceptual graphic, right? And we can now go back and see, is that correct? When I shift 1 downstairs, we can pick maybe rank 2, for instance. For rank 2, we say source is 10, right? That means, in other words, 10 will send us something. That's also here. What we expect is that the destination should be 6, because, as the graphic suggests, of course, to go lower in the communication, I then basically do a, kind of information exchange down there. So I send basically to this destination while I receive from this source. And I think this information is absolutely correct. Rank 2 coordinates are 0.2. I mean, there's also row 0 and 2 is also fitting. And then, we send just some value basically over the wire. So this is then exactly how we thought it should be. Hence, this was working. And you see that we never really thought about any ranks or something like this, and to really paint this. This is more like, for you, kind of validation now, right? That sort of I can find out from this environment when I am, let's say, executing parts of the source code, and I use the kind of different cards here that I also explained to you, of course, in the slides a bit more bolder with this coordinates to obtain the process coordinates from yourself, as one of the 12 executing it. So sort of unique as well. And then you do a shift and say, how would be, the ranks now in this Cartesian topology, depending now on where you want to shift. So in which direction, right? So this is something where we here go 1 below. And in order to do this, I get the source and destination, which was now for rank 2, for instance, 10, while we want to send, receive then, of course, to essentially then, we get basically the send receive to the 6 we sent, and we receive from the 10. And this is what we put in here. And important is, of course, you see also that we remain, of course, in the Cartesian grid, which is an important factor on this. Right. So what I also wanted you to show is a bit is, of course, also the different periodic things that you can do. So we basically said now, that is always going now downstairs, so to speak. But you can here also have essentially the idea of doing, the periodic aspects to different, directions. I think that's quite easy. It's sort of a kind of indicator that you have to specify there. Then this MPI card coordinates, we have already discussed that you basically get your own status in the big grid. The card shift is important, that just obtains the rank of them, but doesn't do it, right? And here upwards in dimension means down. That's here what we had with the aspects of essentially having this then computed always to the the direction. We can of course change this also, or do several shifts, right? Which we also will do in one of the examples. Now, periodic versus non-periodic standard shifts, there's a positive shift in one direction, a negative shift. So this is, again, opportunities and possibilities how to do it. There's just one interesting element. Of course, if you have a non-periodic one and you specify it, there's a sort of problem, right? Because you're not going around in the grid as we had here, right? So here with periodic, we can go again and again and again through it. When we would specify it's a non-periodic, then we need some indicator of saying, now we stop. Let's say we're reaching the beach of the ocean, right? Or another continent. So now our simulation should stop. The boat should not, let's say, go over the beach, because that's not possible. Hence, for us to note that there are some changes, there's so-called a dummy process called MPI proc null, so that I know that, when I do the specific shift, I will find out, hey, there's sort of a, not really a rank, right? This is now important to understand. There is no rank behind this. That's why we call it dummy processor, but as an indicator that the next shift would be, let's say, stupid, for instance. If you want to make the information that the boat goes from tile A to tile B, and tile B is a beach or sand where the boat can't go, then you can basically realize this by MPI proc null and understand, okay, the boat should stop here. Of course, this all depends on the application logic, right? The boat is just one example where it should be an analogy why you probably want to have something like this. Not everything can be periodic. We have discussed the send receive, which is, let's say, send and receive in one. It's also no big magic. You have to still, you see here a little bit the API. Of course, you have to give in much more information because you're sending and receiving, so to speak. You need, of course, a source and destination, but then also, of course, the information that should go over, which is here twice. You see an MPI integer is what we send. It's also an MPI integer what we receive. And the source and destination I got, and this is now the funny thing, without knowing anything, because this is what gives to me via the nice environment from this card shift in preparation. And because I'm executing it 12 times, right? So this means now we have all of these different outputs for each of the different ranks, because every rank will execute it. This, let's say, more trivial source code, all of them will go to the same direction as indicated here, and then we'll report this information according to what you see here. So in this sense, Cartesian communicator, also simple, not blocking communication. So we had non-blocking communication. This is not non-blocking communication, in other words, blocking communication. Hence, now we had the Cartesian communicator. Let's combine both to make it a bit more interesting. And this is sort of a first stepping stone really to a real interesting application where you then could really start essentially of doing this. But before we go there, that's true, I wanted to show you one more thing. And of course, this should be done in practical terms. So we talked about that the grid, of course, was 3 times 2, and I was forgetting this a bit, sorry. So then what happens when we would do 11, for instance, right? I mean, this is sort of almost obvious. And I don't really have to recompile my C code because it's 12. That's what I want to demonstrate here. But my job script is just 11. So how you do this if you now say you need 12 processes or tasks really to fill this grid, right? We could say, okay, with 11, we could 0 to 10, not anymore 11. We have just 11. So 4, 8, 11. Hence, we expect something that is not going to work, right? Because here we see a good example that the Cartesian communicator needs a bit more massaging also via the job script, because somehow the amount of processors need to match, the number of tasks need to match to the, let's say, Cartesian communicator. And when we now look in, we already see some fishy output here, much less than we expect. And here we see the error occurred in this MPI card crate that basically, you see it here, 10 more processes have been sent, but essentially saying it's not matching, right, what we have here. And there cannot be just a creation of this Cartesian communicator. In other words, the complete job was failing. Now I can repair this smartly, very smart of, doing here just a 12. But you can imagine with, other amounts, it would be also a problem. So when I have repaired this here, we can, execute it again, and we will properly get the same output again. The 0 is here good learning experience. When we are too fast with this, we see that basically the job has been not done yet and not written into it. But if we repeat, you see now that the job has written in the output file, and we probably see what we saw before with all the nice and beautiful rank information. Yes, so Good, the remaining parts. So this is just a slide captures exactly what I demonstrated, so I will not talk about this much more. And also the output we have now tested, validated. Let's go to some interesting idea how you can now really start a simulation code. And in earlier versions of this course, people have done a fishing simulation, for instance, as one part of the assignment. Here we switch now a little bit this year to this industry projects and so on and other elements of the course. So we don't do the fishing simulation really. But still, having this code and experimenting with it shows you quite nicely how a real application could be. And the real application has an environment, and we pick here the ocean, right, for fishing, for instance. But this means also that one grid part would have, let's say, an up, down, left, and right partner, right? Let's assume the size of the Cartesian would be 16, so 4 times 4 of the ocean here somewhere. Hence, we will define a little bit this buffer information with this MPI proc null variable I was already alluding to before, indicating essentially for us here that there is a shift that is maybe stopping. Then we have the neighbor arrays that we have with 4 pretty much defined, right? We said, okay, it should be 4 neighbors for one. It's also clear the dimension of the Cartesian should be 4 times 4. And basically the priority will be defined here. We create an MPI communicator again and having, let's say, then a request and stats and so on. So this is a simplified demo code here. And let's go a little bit into practice when we go to the real code. Obviously, there's still some application logic missing where then the fish population has to be transported or things like that. So this is just the general, let's say, look and feel of this, where you now would do some work with MPI communication and so on. And so on. This is something what we, not do, exchanging simple data with old data with neighbors or so, right? So here we do the following. We basically have this, shifts with up, down, left, right, and this determines, in other words, the grid and our neighbors. And because we can, prepare the shift in different directions, we can also understand that this is given to us then. In other words, without knowing which ranks they will have, we will be able to get the ranks through the environment, right? By just specifying up, down, left, right. And this is beautiful for us sitting in the middle of the ocean, right? And then when we go lower here, we see we want to exchange some information. We have this kind of 4 times because these are my neighbors I will go through, right? So I have 4 neighbors. And here you see I do a non-blocking communication now. I send to a certain destination that I actually just got out of the card shift, right? Basically. So in other words, again, automatically given through the MPI environment, I got my neighbor as a destination, but I also got the source as information basically out of the neighbors, right? To basically from who I get information sent. I put that on the slide a little bit with some message exchanges here. You see that. So you see the first part is really, I send my information to my 4 neighbors. And then the second part, the I receive, is then, I will get something good from all my 4 neighbors. And, that's not so obvious if you think alone. Now we have to think a bit bolder and think about that this will now be executed 16 times with, different ranks. And they will have, of course, then also the job to do, not you alone as one processor, the 16 others or the 15 others really have to do the same thing you do, right? So in other words, in order to communicate with you, we need some, communication. If you remember, a send needs a receive and a receive needs a send. And this will be executed then from others around you, from these 4 neighbors, which have some rank we actually don't know per se, because this is given to us from the Cartesian world. And of course, we specify this. Hence, we're talking about 4 and 4 exchanges in a non-blocking way, meaning for us, we have to wait for all of these 8 requests that we specify here in the array. right? Depending on the loop index. So we always go 1i, and having, you know, these 4 requests for send and 4 requests for receives to be weighted. And now in a real application, you maybe would do a loop here, right? And would do a time step loop and say, okay, let's exchange again. Let's exchange again. So the pure information exchange that you see here, what we, you know, have here in the source code, is of course something now to just exchange and print out then here the ranks that are received, you know, who is my left up and so on. This is of course one thing, but normally I would really now calculate the fish population, would send this over the wire, right, to my neighbors or to some specific neighbor, or, you know, in one direction. Now that is really application logic dependent. But here you see also a nice example of synchronizing from all of the non-blocking communication, which is very beneficial because it might be a bit different load if I have to calculate fish, depending on how much fish population I get from right and left and so on, or I got nothing. So maybe a simple calculation, which makes my job much easier. I'm much more faster done, but the others don't have to wait because it's a non-blocking situation. I hope you understand that. I mean, it's a bit, I know, one of the more complicated examples, maybe starting with real application ideas. But let's see and submit this when we do the Cartesian, you know, idea here. We have 16. There's also no secret. We have defined it as a 4x4 grid. So when we SBatch it, we suggest to get some output of our neighbors out by 1 iteration, right? So when we now see that we have this grid part here, the 12 is our job script here. We see we get the neighboring information out from all of them. And of course, then I can do something with it and can say the boat is going always to my right neighbor now. Or, you know, let the fish swim over the different tiles, which was sort of the assignment in earlier times. Hence, what's missing here now for a real application, you would say, this is a space where I do now my nice loop. At the end, I've synchronized, every request is finished, time for the next iteration. And that's where then, you know, the status over time comes in, where you would say, essentially, this is all what I also demonstrated to you, but this is where you over time, by doing just this communication, but you execute it 16 times, can put a variable, you know, and inside this with some logic of saying, for instance, a fish is swimming through this ocean in one direction, which you still have to implement because here we just have an information exchange, right? So you still have the logic to do, basically, and to make this. Here's a bit an example again, when you take different examples out of this, how that looks like when you see that again, when you are rank 5, then we want to see that my top is actually from 1, my, you know, bottom is 9. Sort of you see here the information has received 4 and 6, which is accurate here in this case, and shows you nicely that this actually works. Right, so, and it's a periodic one. And in a way, that's also already a lot, I think, for today. And of course, now we would proceed in normal MPI tutorial to really create such a simulation much more in detail. But as we have also later OpenMP and other aspects like machine learning, deep learning, we cannot go into all the details. This is also not a lecture or let's say a course all on MPI. We have many different facets in HPC in this course with a CFD special even. So in this sense, we keep it to this degree, but we encourage you also to really go to one of the centers, to the UHPC undertaking, the National Competence Centers, to find more on MPI examples and tutorials, which would be maybe material that you have for a whole week instead of just one lecture. I hope it was still useful for you. Thank you very much. And we talk to you next time with lecture 3.